Sir, good afternoon. Can you hear me now? Hello.
Sir, good afternoon, sir. Shall we start, sir?
Yes, sir. Can you hear me
Yes,
now?
sir. Yes, sir. Now voice is clear, sir. Yeah. Yes,
Good afternoon. Good
Yes, sir.
afternoon, everyone.
Yes, sir. Okay.
For the
to
next
start.
session,
Good afternoon, sir. 1 minute, sir.
good afternoon,
Yes, sir.
everyone. For the next session, we have Sidhu D. Sudarshan for handling cyber security topic. Dr. Sidhu D. Sudarshan heads the Center for Development of Advanced Computing, CDAC, Bengaluru. Prior to joining CDAC, Dr. Sudarshan was with ABB with focus on industrial software systems, heritage engineering migration, analytics, and cyber security for about 8 years. Dr. Sidhu D. Sudarshan has nearly 3 decades of research and development experience with leading national research and development agencies in India as well as United States. His areas of specialization include information assurance, network security, cyber physical systems, sensor networks, safety critical systems, semantic mining, and analytics. He is a recipient of several research grants in the area of information security. Dr. S.D. Sudarshan has participated in several standard committees at national and international levels. Before joining ABB in 2012, Dr. Sudarshan was with US Food and Drug Administration as a visiting scientist leading their semantic data mining research and development program. Also received FDA Outstanding Service Award for his contribution in the year 2012. Dr. Sudarshan has a PhD in Applied Computing from the USA and awarded Outstanding PhD Graduate Award. He has over 100 publications and filed 10 patents. Prior to joining FDA, Dr. Sudarshan was with CEDT, ERDCI, and CRLBEL. Over to speaker, Dr. Sudarshan.
Sir, good afternoon to all of you. Very nice seeing a full house of 30 plus people. So at the outset, let me first thank Dr. Sitaraman for following up personally and pulling me in this ATAL FDP program on VLSI related things area. So yeah, one way we could have gone into security only for VLSI perspective, but I thought, that is your core area. I will touch upon it a little bit, but I thought as an overall thing, as industrial scenario is evolving with Industry 5.0 and digitalization, we should have a little bit larger idea on cyber security as we go more and more towards Atmanirbhar Bharat, and we have more and more disturbances both economically in digital world as well as physical borders with the country. It is very important to know where our industrial technology is also going, and so that whatever you develop in VLSI, our own ASIC or FPGA or IP core is relevant from the application point of view, from end user point of view. Because when it comes to only the chip and basic theoretical part, I think you are the masters, you are all the faculties. So I come a little bit more from industrial background. So I thought I will bring the concept of applied part here in the next about 70-75 minutes. And then maybe we can spend another 10-15 minutes on interactions. Of course, I have no problem interacting in between. Just in the interest of audio and echo, request all of you to put it in the chat box if there is a query, or raise your hand in the digital way, so that there is less echo and everybody can benefit and make use of the time. So with that said, probably I'll get on to the topic. But anyway, it is very good to see IIIT Tiruchirappalli Srirangam coming into big stage. And I wish them, they join the big league soon. of already traditional triple-ITs that are in place. So having said that, let me share my screen and then go from there. So in case anything, before that, quickly, anybody wants to say anything, please feel free to put it in the chat window. And in the interest of the bandwidth, I'll keep my video off during presentation and I'll switch it on again towards the end when we want to have a few questions. Is that okay, sir?
Okay, sir. Yes, sir. Okay,
Right.
sir.
Thank you. Thank you. So good afternoon. Just any one person can confirm if the screen is visible, then I'll start going on.
Sir, yes, sir. It is visible, sir.
Super. Thank you. Because I have put it in full screen mode. I have about 30 odd slides. So I'll try to spend a couple of minutes on each of them. So with that, cybersecurity was the overarching theme that we wanted to cover in this session. But I personally thought it is the IT-OT integration, which is enabling this industrial IoT, digitalization, digital industry as we go forward. So from that perspective, I have kind of put the focus on industrial systems and industrial control systems rather than the traditional IT systems and what are the new challenges. Because that also brings in a lot of sensors which require very strong focus on VLSI and related technologies to develop new sensor material, new chips. So they all have to become part of the industrial systems or in the digital environment that we are talking about, or the IoT part. So from that perspective, I thought the focus can be a little bit more on the IT-OT, which is basically information technology and operational technology working together. So if you really look at the evolution of industry, on the top left, you can see we started with isolated devices. And over a period, the fishbone clearly shows we went from, these individual devices got interconnected with a point-to-point, the traditional serial cables and so on. And then small networks started coming up, but they were very, very proprietary because there were no standard body to connect all of them on interoperability. As they figured out individual networks cannot work together unless they have some common protocol, the scale benefit cannot be achieved. Accordingly, the new standards evolved, Ethernet, IP-based networks and all. When the standards evolved, we had interconnected systems. And then once they are interconnected, we evolved into distributed systems so that certain things can be done locally, some can be done in a fully centralized manner, and some can be done in parallel. So semi-hierarchical, fully hierarchical, all those things came into picture. And then over the period, we also developed this point-to-point interface could be, need not be always wired, but could be very much wireless as well. We started using free space optics. We started using RF spectrum to our advantage. So the wireless and remote access got evolved. And now we have matured into completely a cloud-based system where the entire infrastructure is elastic in nature, basically. So to make use of this elasticity, the devices needed to become smart, which we can call them cyber physical systems, if you want to call it that way. So today we are looking at smart devices, which can make use of cloud-based systems that can help us go to the next level of digitalization or human evolution in technology. So if you really look at it, what we are looking at today is all the control systems, whether it is a car that you want to be driverless or a home that is smart, where you can control your room temperature or your kitchen appliance while on the way from office to home or traveling from one place to another place. The kind of remote control and automation we want. So that's what is the theme, or I will say the goal. But as we speak today, typically most of the automation we are trying to do with commercially off-the-shelf IT components. And then we try using standard communications. And they are highly interconnected, and mobile devices have become part and parcel. So, but as we connect, for example, an automobile or a smart appliance in the kitchen, they are actually very specialized systems. A microwave oven, for example, or a baking oven is not like a traditional computer, but still we use the protocols and the interconnectivity designed for a traditional IT to a control system, which are actually specialized hardware and software connected to a general purpose hardware and software. So that creates a new level of heterogeneity in the system, but the heterogeneity has to still answer existing IT-based infrastructure requirements. So that is throwing a new set of challenges, which is really a very, very good thing for us, because unless these new challenges come up, we will not have research problems and our job will be at stake. So the requirement of engineers and the R&D will continue to remain there thanks to this heterogeneity that got introduced because of the control system getting integrated with the IT systems. And if you look at it, as we connect two things, they start seeing each other. So the risk and vulnerabilities also get transferred to both. So to say, the threat surface from normal IT systems gets extended to this control system that get connected here. So the question is, should it really matter? So the answer is, looks like it does matter. So I have put it in a very simple table here. A traditional IT system on the left-hand side and OT or operational technology on the right-hand side. So in a traditional IT system, we are actually looking at protecting the information or the data. Whereas in a OT system, we are trying to protect the physical process, which is quite different from just protecting certain numbers by encrypting and putting access control. So in a physical process, there are a lot of issues. So the protection is not just encryption based. And the risk is primary risk impact. In the first case is probably some secret gets disclosed, could be financial, for example. In OT, it is not just the information, but it is the safety, the health, the environment, even the financial. For example, the physical process of braking a car, a Zoom car or a Google car driverless you are running. If the brake doesn't get applied appropriately because of some security risk or threat that got materialized, then it is not just about financial part. It is about safety of the vehicle, safety of the passenger, safety of the environment as it hits some, gets into an accident. All those things become very relevant. So the focus on security also in the IT is about where the data is stored, the central server or a database server, where it's a kind of a star and hub model, hub and spoke model. So wherever there is a central node, the server part, which requires strategic locations, which require focus. Whereas in OT, it's on every device. Each one has to be completely stable. You cannot say the Tesla control center is to be protected. It should be each and every vehicle, Tesla car has to be protected. If you are looking at a smart kitchen, each and every appliance all over the world has to be protected, and so on. In terms of availability, compared to IT system, the OT requirement is much, much higher. Ideally, one would like 100%, but at least of the order of 99.39 to 59 depending on the infrastructure that we are talking about. And this also can be seen in terms of how deterministic the system should be. In an IT system, it is okay to have minutes to days to get a stable state. Whereas in a OT system, we need to be happening that in milliseconds. At best, it could be in a couple of hours. So the time to react is also much shorter. The environment is interactive and transactional in IT. In OT, it is interactive, but it is real time. Many times it is hard real time, not just real time in the soft sense. In an IT scenario, we can reboot, we can restart. In a OT, it is not possible to restart. So we have to build in fault tolerance, resiliency, online repair, and so on. So those are big challenges that OT faces. So if you look at combination of IT and OT, they are similar in terms of requirements, but they're quietly different in terms of character. So the characters that define are based on the availability, performance, and the accessibility. And also in the OT care, the failures may endanger employee, public, environment, and so on. So when you expose same kind of threat environment that was sufficient for IT, may not be sufficient for OT. In fact, there will be new aspects which were never thought of in IT that will evolve in OT side. So the question will be, if there is so much risk in merging these two, is the integration really required? So that is what I'm trying to show with a set of kind of protocols, or the way things work. If you look at the top, that is the enterprise zone or the IT zone, where you have logistics, you have financial systems, you have learning management, content management, and so on, or your movies, YouTube channels, and so on. So all of them are, you can say, level 4 and 5 if you take a zone approach, various levels of close to the physical process to aware to the IT process. So there it is generally network protocols like your HTTP, DNS, DHCP, they all will be sufficient. If you go to the bottom, we are looking at, okay, let me try to get a pointer. So if you look into the safety zone, which is actually where things are happening, a production line and things like that, they are safety critical. We apply a brake, it should work within a certain millisecond. You want to open a valve, the chemical or the water should flow immediately. And similarly, a gas should immediately start flowing, or it should stop flowing on closure. So these are all safety critical on ground. So that is where process control comes, which we call them level 0. So this is the area where typically OT works. And little above the process, we have basic control, where you have, this so-called relays and things like that. And then at a line level, we have a supervisory control. And in a plant, we are looking at a manufacturing zone. So these are all on the OT side. And there are specific protocols like Goose protocol, IEC 61850, and then there are field bus and Modbus and so on. So these are all the OT side. But somewhere we want to control, let's say, what is going on, like vehicle controlling for that matter. I want to control it from the enterprise network. So that is where the whole challenge is. I have a cell phone to talk to my friends, to talk to my colleagues. But today I'm using the same cell phone to control the geyser being on at home just before I reach, so that I have warm water readily available. That I'm trying to control something which is managing a process where a heating element has to be switched on, and there has to be a sensor that will sense the temperature, so that at appropriate level the heating element gets into stable mode, or switches off again when the temperature is enough for the water you have set. So we are trying to connect these two, and the protocols are totally different. As you can say, one can be HTTP based to the level of Goose. So some of them do not even have an IP address. They go by the frame address and so on. So that is where, we want an integrated network. That is why the integration is happening today. For example, we don't want an operator standing in front of a reactor to control a process. He should be able to control it from wherever his cubicle is from an AC room operator control station. Today we are talking about metros where it is run driverless operation. So whoever is driving the vehicle, they control it from a control room without being part of the actual engine, which is driving the vehicle loco. So that is what requires the IT/OT integration. So the benefits are, it is easier, it saves time, and it is more safe for the humans because you are away from action. Think about a cement plant where the entire plant can be managed without getting into the plant because the plant is very noisy, very dusty, and then a lot of pollution. All those things are there. By staying away from there, it is good. Second, many times the industry is far away from cities. Offshore drilling of oil and gas. In rough sea, something is happening. So it is very expensive to have people there, operators going there and working. It should be managed from remote. So it does help in a lot of things. But the biggest challenge is as we integrate these two, real time and non-real time, and also logical with physical activities, we are getting into common cybersecurity vulnerabilities, and they get actually complicated. That is the biggest challenge we are looking at. Okay, so that is the reason the motivation comes. And if we put it from a network diagram, this is how it can be seen. And as you can see, there is an industrial plant right at the. One second, let me change the pointer option. Okay, so it is a slightly better color. So at one end, we have the industrial plant where actual process happens. You can see there is a plant, there is a shop floor, different types of plants. So they are all managed through devices which are sensing the temperature or pressure or the heat or the radiation and so on. All these are connected to a controller, and they get to a common point through a gateway, and that is managed by the SCADA platform, the supervisor sitting here and so on. And this industrial plant has a common platform, which today could be a cloud. It could be at the enterprise level, but at a high level, we can say it could be on a cloud. So this platform, which connects both the IT layer on top and the non-IT OT layer at the bottom, which is on the enterprise layer here, could be the IoT platform. So as we do this, at each layer from top to bottom or bottom to top or left to right, you will find there are totally different types of security issues. In an office LAN, we are looking at a certain kind of files and approvals and confidentiality, strategy documents, and so on. Whereas if you look at the analytic app, so there is someone working on the business development, trying to which client to go, how to pricing strategy, and so on. So here something else is happening. And then there is some operator who is actually remotely controlling all these sensors, actuators, entire plant is run through them. And in between, there is a system, which is the IT layer, who are providing the IS services, who connect each of them and ensure that, there is a demilitarized zone, militarized zone, and so on. So that is being taken care by these people. So in one sense, there are certain things that are managed by the plant owners because he owns the entire plant, but the plant is consist of various components. For that matter, each of the area has different components. These components are built by different people. And component builder has to do certain activities to ensure security. Plant owner has to do certain things during the operations to proper configuration, management, monitoring, and so on. So if you look at it, VLSI comes right into this component builder part, where we are looking at a lot of VLSI-based designs, where new chips are designed, IP cores are designed. So how do you ensure that you address the security aspects at that level? So that is what. On the other side, we have system integrator who is connecting all these industrial plant, IoT platform, enterprise tier across, and he built a magic web, digital weaving of the things, and then we go forward. And once all these things are happening, the infrastructure critical systems and the IT systems they need to work together. So the focus for one of them is the availability, because we want, for example, electricity to be available. Confidentiality is not that great. Others need not know whether power is there or power cut is happening. I don't mind if somebody knows I have electricity at my home or office. Whereas in IT system, I am worried if somebody knows my bank balance or not. So like that. But in the emerging integrated scenario, we want both availability and confidentiality to be simultaneously ensured. And as all of you know, as things become more available, it is more difficult to ensure confidentiality, because secrecy is maintained, the less it is shared. So the less available a system, there is a chance of higher confidentiality being maintained. So there are conflicting requirements, but we have to manage. So here the challenge is, how do you build trust between a component builder, plant owner, and system builder? We saw the three guys in the previous figure. Unless they trust each other and certain parts are done by each of them, and then there is something, integrated way it works, security cannot be guaranteed. So these are all, putting that, there is a part level security. Each component builder who is providing service has to provide certain kind of security, but yet some of all these things cannot actually make the complete thing safe. Still, the interconnectivity or the mesh that connects all the components which are independently safe, so also remain safe when they become a system, when they interact with each other. So the system level security also has to be, the umbrella component also has to be built in. So if you really look at most of the attacks that have happened in the past, many of them have happened for things that are absolutely not related to purely technology. So maybe I can take something very simple, the Ukraine power cut, which happened a couple of years back. The funniest part, or if you go a little bit in detail, at least there is evidence to show that the attack was actually in one sense not related to OT per se. Apparently there was some script, the way we have got ActiveX script and all that run when you download certain things. Apparently some script slowed down a certain kind of word processing software, because of which the screen that was monitored by the operator on the performance was not getting updated. Rolling in a car and the music is being playing and you are adjusting, you are searching for a channel. As you work on the music, that is taking your CPU time, and your accelerator or the speedometer is not showing that vehicle is increasing in speed, even though you are pressing the accelerator. But basically, your CPU cycles are stolen by the entertainment software, whereas it is not able to update your speedometer. So what happens? You try that, what is going wrong? You try to accelerate faster and faster. Your vehicle is actually traveling at, let's say, 100 kilometers per hour, but the speedometer is still showing only 40. Your CPU is busy with the entertainment system. So you accelerate beyond a point and it crashes. Something like that happened in the Ukraine case. The word processing software was delaying the update on the screen, operator screen. So the operator thought certain things are not happening, so the control is not happening. So they tried to do manually control, which means something that was locally done, he was trying to take over remotely. That means your CPU is already busy doing some scripting, which is not updating your screen, but you are adding another task of controlling a system from remote, which means you are further overloaded. So ultimately the system crashed. So many times the OT failure can be simply traced to a basic IT failure. That is what happens. That is the reason the IT-OT integration has to be taken in a holistic way, and we have to take things in the right manner. So we can also look at them from a various domain perspective, application, business, operation, and sensing, actuation, and so on. But this is just for the sake of putting in a slightly different way. So when we really look at the industrial IoT, as I call it, the moment you integrate IT and OT together, there are several challenges. The first of the all is supporting legacy devices. Because if you look at plants, whether it's a steel plant or a power generation plant, hydel plant, they're all pretty, aged. They were done in 1960s, 70s, 80s. They're still running, producing the devices, producing the components, producing cement, producing steel bars, and so on. But they have a large number of devices. They have been running for so many years. So since there is something is running and giving profit, there is no need to replace them. And they were not connected. They were not designed to connect with the internet or anything like that. They had, as I said, proprietary protocols and so on. So the entire plant was controlled through physical management, physical access control, and so on. And then there is also a new requirement of connecting these old devices to the new system, because I want to upgrade the plant, make it work. And sitting in my place, we want to know exactly what is the production happening today. That means the devices that were not designed for interoperability, we are putting a wrapper kind of layer, or we are putting a bridge or a gateway to connect. So one-way connection is still somewhat okay, where it just uploads. But the moment you want to control, it is a closed loop. The moment it is closed loop, the legacy design does not cooperate with the current design, the new way of working. So the protocols don't support the speed and things like that. And then we are also looking at coexistence of both wired and wireless protocols. Yeah, one side, as a person, we would like to have a wired infrastructure so that, the RF noise is minimum and the things are much more reliable. At the same time, we want to be able to agile and mobile, which means wireless also needs to be supported. So the challenges of reliability of a wireless protocol in an industrial environment is always a major thing with packet loss. So how do they work together? That is another challenge that we need to address. And then the computational capabilities themselves, because making it smart means there is a CPU, some kind of computation happens. So how do you manage the disparity between a low-cost sensing device, extremely lightweight computing, to a key management infrastructure for digital signature, where we are looking at a private key, public key, high level of homomorphic encryption, quantum safe encryption, and so on. So this disparity also needs to be looked into. So if you really look at it, even though we call it IT OT at a high level, it is about a timeline management, legacy devices to the current technology, wired protocol versus wireless networks, and low resource or resource constrained sensors and actuators to highly resource available servers and cloud kind of infrastructure. So it is basically saying that we want to have a continuum without a digital divide, when we know the technology has things that have to support both 0 and 1. So the digital divide has to be overcome. That is what it comes to in the end. So if you really think, why don't we ignore and go forward? That is extremely difficult. The legacy systems in industrial control alone, it is almost 65 billion installed market, which are more than, if you look at it, almost all of them are more than 20 years old, which means we cannot just ignore them. It is almost like we have extremely good quantity of jewelry, but that have old designs and outdated. So we have to, old is gold, as we say, but the gold is old. That is also a fact. So we also want to get the gold renewed. So we want the value of the gold, but it should be modern. So that is a challenge that we need to look at. And when that is, for that, as a technologist, as a R&D person, as somebody who is into academics and research, we need to we address them by compartmentalizing things into something that is chewable, because each of you is specialized in a particular area. So when we want to specialize, we should be very clear on different layered architecture. That is what we do. So we will look at into how do we handle this communication challenge through various system layers, field devices, cloud, and some initiatives. That is how we will go forward. So I will start with the field devices and clouds, because in the end, whatever I showed as a level 0 to level 5, or physical process control actuator to the IT system, they all can be put into simply this kind of 6 layers. So at a high level, we have cloud, which is completed digital, virtual, what to say, the information highway and superway, as you would like to call them, with a web of web, www, social web, digital web, whatever you want to call it, energy internet, industrial internet, name anything. End of the day, it is a digital industrial, information infrastructure. And on that platform cloud, we have operation center, which control the entire system. And to control them, they should be able to communicate. So we have a communication layer. And where do they communicate? They need to communicate, they need to get certain information from the sensor and actuator. That is done by intermediate layer called the field computing. For example, you want to get the average temperature for the last 3 minutes. Or in a particular room, what is the temperature of the entire room? That is what we want. Not each corner, what is the temperature? That doesn't work. So certain kind of field computing is always required. And below that, there are actual sensors and actuators, which actually work on physical process. So this is the way the layers can be thought of. And the purpose of this particular slide is immediately you can put where your expertise lies. If you're actually a core VLSI designer, probably you would like to say that, okay, I'm into sensors and actuators. That is what the layer I want to focus on, perfectly fine. Or, I want to have an ASIC, which will do not just the sensing and actuation, but it will also do a little bit of computation, including some calibration and things like that. Then you are looking into field computing also as your option. Or you would like the ASIC to be also able to communicate. So you want to provide maybe a UART port, universal asynchronous transceiver, and things like that. Then you are immediately looking into communication as well. So it all depends on what layer you want to work, how much of integration you want to do. But end of the day, this layered architecture helps us in many ways. So probably I'll skip the physical process part. The screen I have shown mainly just to give a context that whatever we call OT, they can be in diverse environments and they can be anywhere and everywhere, from a simple sewage water treatment plant all the way to mining to minerals and so on. So I'll go forward. And just I'm showing one particular figure here, just to show that these things are not small. For example, a simple FLNG plant, which is used by Shell, which is one of the oil and gas guys. This particular vessel that you see has located inside the deep sea almost 125 nautical miles away from the nearest land. That means it is in the rough sea, with Nivar being talked about hitting us in the next 12 hours or so. You understand what it means to be in the sea with nowhere to anchor. Okay, but the size of this is almost like a 4 soccer field. And the point you would like to say is, this is the lifetime is about 20 to 25 years. And this particular thing has got pretty much the sensors which run into millions. So that kind of communication network that is inside, they need to talk to each other, each sensor, actuator, and so on. So it has 14 production facilities inside this, which means we have 14 factories running inside this. That much of complication it is. On top of it, to support all this, there is a complete power generation unit, which is probably larger than a microgrid generator. So you probably have a 2 or 3 megawatt power generator station, primary, another 2 megawatt secondary, and then there is an emergency of maybe 500 kilowatt, and then there are battery backups and so on. So all these things are part and parcel of this one independent thing. Okay. So when you look at these sensors and actuators, contrary to what we think, the sensors, we all know about temperature flow, but not everything is just a sensor like that. Even an encoder, an analyzer, they are all sensing elements. You sense and analyze. Particularly if you look at air pollution, we should be able to today find out particulate matter, PM 2.5, PM 10. There are analyzers, they are not just sensors. Because they have to find out the particulate matter over a particular volume. It cannot be just whether there is a particle present or not. So there are standards. So quite a bit of things that are there. Similarly, actuators could be many, from pump to valve, drives, turbines, heaters, coolers. A large number of things are involved. And all of them, you can take it from me, have a number of things that come from your VLSI background, because they're all embedded systems with certain chips in them. And these sensors and actuators, however simple they may look like, they have a complete life cycle. So you can start from anywhere. So in the beginning, you have to set up the sensor to work for something. So the moment you set it up, this has to be configured for a particular operation, whether it is a 2-bit or 4-bit, 3-wire communication, 2-wire communication, point to point, point to multi-point, and so on. Then this has to be deployed and then operated. During operation, somebody has to monitor. Why do you monitor? Not only for the process, also for the sensor, we have to continuously diagnose. Is there an offset? If there is a drift, is there a jitter? Are the readings still, deterministic and reliable output is coming? All those things, sensitivity, selectivity, they all need to be continuously monitored. And then further, we also have to look into servicing to ensure that. Yes, please. So we have a complete life cycle, even for a simple sensors and actuator. Okay, and then we look at the field computing level. What could be a field computing? This could be simply a step execution. Like, you want to do a polling. I have 10 sensors. I want to read each of them one at a time. So that itself could be a simple step-by-step execution. There could be a control loops. There could be device scan, which I mentioned. Polling could also be one way to scan devices. But it need not be always sequential or cyclical. Some could be time-based, some could be event-based, and so on. And then we should be able to detect faults. We should be able to generate alarms. We should be able to convert from one type of protocol to another type of protocol, and so on. So they all could fall into the field computing. Typical things are, input-output units, controller units, programmable logic controllers, RTUs, controllers, and so on. If you reach the communication level, we are looking at something totally different. It can be Ethernet and serial, which is very common, but it can go all the way up to current time-sensitive networking and cyclic versus exception, and so on. And this is what is used in the field at the working level. So there are hundreds of protocols. If you thought, standardization is easy, all these things that are listed here are actually part of standard. So that is the reason we mentioned about protocol conversion as one of the requirement in the earlier slide. So I should be able to work from remote IoT, a device net or device net to Profinet, and so on. So those are things, hundreds of protocols, and they are still at layer 2. Layer 2 means media access control and data link layer, which is very much in the realm of chip designers. And then if you go one level up, then we are looking at time sensitive networking, and which can support a number of things. And we have OPCE kind of standards that are coming there. And then a little higher level could be the network management. And as you go further, we can have a center, data center, cloud center, and so on. All these are possible. And if you go further, we have operation center where the operators take care of the entire plant. Instead of standing in front of a physical plant which is hot and humid, you can control the entire thing sitting from your control room. So this is a command and control room, as you see on the top. And at the bottom, what we are showing is how the process flow is actually shown. Here you can see water level increasing, decreasing, and so on, and various alarms and various settings the person can keep watching. So these things are to do a lot of analytics today. People are talking about cloud, but interestingly, these clouds also nowadays talk to each other. I can have some part happening in Google Cloud, some can be in Azure, some can be in Amazon, and so on. But all these things come with their own cybersecurity issues, and we'll go forward. And here the challenges will be, we want a public cloud versus open on-premise cloud, service level agreements, what kind of security, compliance to law enforcement, including privacy requirements. Are you logged into with a particular vendor because porting is very difficult, and so on. Those are the challenges. And of course, in spite of that, people have found the standards way of interpreting. For example, FDA Alliance ensures, field devices talk to each other, and then we have OPCA, which can connect to processors, and inter-cloud operations are available through IoT Hub, for example, from Azure, and so on. So these things are slowly getting in place, but if you go forward, in the end, all of them fall into this kind of an architecture where there is a transport layer, there is a data model, there are a number of things starting from profiles to concepts, and how discovery happens, and so on. So there is a complete thing available. And similarly, field device integration guys, they have come up with their own things, various kind of FDA server and how they talk to each other, what are the things. And now more is another open architecture where, from the things, IoT things, all the way up to monitoring optimization in an open and secure way, they are available. And as you can see, a number of vendors are already providing solutions here. So with all those things, open things, which means a lot of things are configurable, lot of things are not very, very clear. So this can happen, result in various kind of threats and vulnerabilities. At one end, they can be at the device level, hardware related, the boot sequence, interrupt sequence, then operating system related issues. Because more and more clouds are coming, we are looking at hypervisor related thing, separation of kernels, shared memory issues, a number of things are coming into picture. And similarly, when it comes to at the network level, we are looking at the communication related things, man in the middle, spoofing, eavesdropping, credentials compromised, privilege escalation, and so on. At the monitoring stage itself, what happened, the policy change is not applied till the last device because of some communication or lack of connectivity issues. Or is it that, you made a policy change globally, but in a particular country that is not allowed? So how do you handle exceptions? How do you roll out uniform policy? How do you handle multiple policy requirements? And then how do you manage configuration? Because the patch management, configuration management, they are all big challenges. And what happens if there is a breach? Who is in control? The attacker or the owner? So those are big challenges that we are looking at. So what we need to do is, like we converted the entire requirements to various layers, from field computing to communication to cloud, all the way up from physical process. We also need to build security in various functional blocks by having a framework. The focus for you could be device security. Here we are looking at physical security. We are looking at identity and access control. Here we are looking at concepts like trusted platform and things like that. And then we have to build communication security. We have to look at security for the monitoring and analysis, where intrusion detection can happen and things like that. And then configuration management itself. What kind of security settings are made? Are we still supporting SSL 1.0 or are we ensuring TLS 2.0 is complied with? Are we allowing HTTP or HTTPS and so on? Similarly, data protection, both from privacy perspective, also from encryption and secrecy perspective. And then code security itself. Today, one of the biggest thing we have is the code itself can be compromised. So we are looking at static and dynamic analysis tools which can take care of code security related aspects. So maybe I'll focus now a little bit on, with all the background in place, what is it that we have various challenges and opportunities in this area. So we can look one at a very, very high system level. So there we are, what we are looking at is, today we do not even have simulators because of such a complex interplay. we don't have enough simulators, which squarely falls into the academic domain, where you can get student develop simulators. You don't need any infrastructure except some compute facility. And the simulators can be initially software based, could be low fidelity, can become high fidelity over a period of time. Then some components can become hardware in the loop, so you can actually put few things real, rest of the things that are not available into software, sorry. And then where there is an operator control is involved, you can put the human in the loop. And then we have to start supporting industrial control protocol on top of TCP/IP or internet protocols. And then we can introduce additional resource constraints in terms of bandwidth, in terms of memory usage, and so on. Then you can add the real timing constraints, how much hard real time it should be. Then you introduce wired, wireless, and so on. So the simulator itself, it can be a very, very rudimentary software based, but as, yes, any questions? Okay, so it can be very simple, low fidelity software, all the way to a very complex heterogeneous system with all real-time requirements in place. That could be at the system level. The other one that may be extremely relevant, or I think the most apt slide for VLSI, is the design verification. If you today look at it, there are more than 2,000 companies that design chips, and they are spread across countries. And today the way people do is, when we get the chip, we basically look at the data sheet, assume it is correct, and we check for the functionality. But we never check whether the data set is actually reflects the true chip design. The chip actually can have malicious circuits inside, which is not listed in the data sheet or the design guidebook. Are we looking for them? Because even in software today, we are looking at patterns as well as anti-patterns. So many times, it is not the presence of something which matters, it is the absence that matters. So the vice versa. So are we looking at the whole set, universal set of the entire hardware circuit as it is? So are we looking at any presence of malicious circuit? If at all it is present, it is intentional. Could be sabotage, could be espionage, could be terrorism, could be nation state sponsored things. Many things can happen. And then if malfunction is detected, today, if there is anything happening with the testing, we always suspect software because we assume hardware is right. So can we come up with mechanisms where you can know that software is not suspect? The technique is enough to ensure that the fault is not on the software side, but it could be hardware. Today, we do not even have approaches to suspect hardware when there is a system level issues, testing failures. It is always software, it is always configuration, or we feel that the piece is defective. Still, we do not suspect the hardware. We try to replace another module from the same vendor or similar hardware. That is a question to be answered by us. Can we have actually a chip monitor to detect hardware attacks, malfunctions in milli-microseconds? So they can be detected in real time, and they can be, alert can be raised. That is something I think, we need to look at it very seriously, and without which we will fail very, very badly. Another aspect that has not been discussed, or you can say the elephant in the room in the hardware security, is EMP attacks. You may be aware, EMP stands for electromagnetic pulse. The most common EMP attack that we know is lightning strikes, some vehicle gets burned, building gets burnt, or a person dies, or a tree gets burnt. So EMP attacks as a lightning attack is what we know, but it can also be planned attack by us. In fact, there was something that was proven that you can use strong microwave radiation to decapacitate soldiers during war. That has been at least demonstrated. Used or not is still debatable. but it is available. So here an example of 1980s. Actually, a pipeline actually exploded in Netherlands, and it was not a small one. It was a 36-inch. We all know a 2-inch pipe in a borewell, how forceful it is. This is 36-inch. So what was found finally was there was a SCADA system that was controlling the pipe, but there was a naval port which is about a mile, and they had a radar which actually disturbed this SCADA system with this RF and resulted in the pipe exploding. So this is a simple radar which is scanning the system, which is not truly an electromagnetic pulse. That itself can cause an havoc like that. What if it is planned? And think about it. Today, every time we switch on a machine, a switch is turned on and off, there is an electromagnetic pulse or an arc that is always induced. As we go more and more VLSI, which is of a lower voltage, lower nanometer, much more sensitive, they become part of the switches. Their susceptibility will keep on increasing. So we do need EMP simulators. We need designs that are EMP proof. So those are challenges we need to look at it. And then all this, as I just mentioned, these are all resource constrained devices, any wireless sensor network, all of you will agree. So how do we ensure denial of service attack do not happen on them? Because if you look at Modbus is one of the very common protocols. They were designed to run for 19.2 kilobits per second. Incidentally, now that is also available on TCP. It is called Modbus TCP. So your Mac is designed to handle a serial bus protocol at 19 kbps at most. That is the upper limit. But since it is running on a TCP network, TCP IP, the Mac is now hearing a TCP that can be a 10 Mbps, 100 Mbps, or a gigabit network. So the system will just go mad. It cannot handle. It is like what happened when the meter gauge railways got converted to broad gauge and the speed was increased to 120 to 140 kilometers per hour. Lot of buildings collapsed. They have nothing to do with the railway track. They have nothing to do with the railways itself. Just that the traffic created a vibration which impacted so many buildings. It is exactly same when we have a resource constrained device on a highway which is having information bits flowing at gigabits per second. So today, denial of service is the easiest and most commonly used attack on most of the IoT devices, most of the resource constrained systems, so to say. So that is something we need to seriously look at it. The other aspect to look at is the device forensics. Assuming something failed, which always happens, we mentioned about 99.39, 49, 59, it is never 100.0. So when something goes wrong, do we have even capability to do forensics today? We are struggling. We need post-factor forensics to eliminate at least potential incidents in the future. We can have lessons learned and then design accordingly. This is a reactive approach, but at least this has to be done. Then can we have a robustness analysis? As I said, can we check for presence of unintentional circuit in existing products? That is proactive. That is much more complex, but that is what is recommended. Reactive approach is mandatory because at least we learn from the failures and do not repeat. But avoiding failure is the most appropriate approach, proactive one. That is recommended. But we have fantastic challenges to look at it. Today, whatever robustness tools are there, if at all any, they are for IT systems. We need to adapt them for industrial control protocols, for SCADA systems, for specific software that run on top of the IT system. Because today IT system does not, hardware checking guy does not look at the software, software does not look at the OS, and OS does not look at the network, and so on. Each one is compartmentalized. But the flaw lies when these, at the interfaces, when these systems talk to each other. So we need to come up with an integrated, holistic testing approaches, forensic approaches for all of them. And we also need to look at unit testing versus system testing versus module testing and so on. And also we need to test a lot of things while they're in operation, because we cannot take a shutdown. I can say, for example, there are nuclear reactors. A planned shutdown is permitted with typically 3-year notice period. That means you have to plan 3 years in advance what are the repairs we'll do when we get a shutdown for X number of hours. If you don't do it, we find many times, because of the whatever sea algae or whatever it is, jellyfish, they get trapped into the mesh. And when our nuclear plant shut down, because that is unplanned, you will find they are shut down for 6 months, 8 months, 9 months, 12 months, and so on. So unplanned shutdown is not acceptable in many cases. So that is the device forensics. We need to do proactive as well as reactive forensics. A lot of challenges and opportunities exist there. And in the end, if you want to really look at it, cybersecurity is basically a life cycle requirement. This is applicable for anything and everything. So at a high level, we need it at the time of installation when you start the work. It could greenfield means nothing existing, I'm constructing new. Okay. Brownfield means I'm doing an upgrade. And for that, we need completely validated component and subsystems so that I don't bring in anything that is not cybersecurity cleared. It is at the time of installation. But installation alone does not mean anything. The system has to start running. That is the commissioning phase. So that time, it is all about configuration and testing, verification, validation. All of them need to be taken care at the commissioning point. If you really look at it, that is what is delaying, for example, the LCA. How many test flights they need to undertake? Because before they commission something into Air Force, they need to consider all kinds of scenarios: summer, winter, rain, high altitude, low altitude, sultry climate, dry climate, humid climate, daytime, nighttime, transition time, and so on, different wind conditions, and during hostile environment, during emergency takeoff landing. So all kind of things have to be the commissioning and time we need to test, because that is when you want to accept. Maybe they all would have been done at the time of design itself. I'm pretty confident, but you need to really test it in real waters and real sky. So that is why this confident testing is a huge and humongous effort. So that part needs to be taken care. And then once it is commissioned, we need to maintain from the patch management to operational safety. How do we do it? Which patch is applicable for what? Can a patch disturb some other application? Because sometimes patch management patches, when you apply, some existing software will stop working because the version mismatch happens. That cannot be made to happen in a flight or a industrial system or a OT system. Then we are looking at the upgrade part. We are looking at various component level upgrade, system level upgrade, and so on. Sometimes it can be even rip and replace. We want to demolish a particular part of the building and reconstruct. So all this upgrade also needs to ensure that it does not introduce any new cybersecurity vulnerability. At the same time, they are complying with the new requirements. Because always we have something like, for example, today, if you look at it, our vehicles should be BS4 compliant. But if I'm buying new, I should buy BS6. Because of COVID, there is some relaxation. but it is already BS6. That is what we are looking for. So when you upgrade, it is not just replacing like for like. It is like for like plus whatever is the new requirement that are required for that particular life cycle requirement, particular component that is getting replaced. So that way, cyber security is indeed a complete life cycle requirement, and the entire thing is important because today we are becoming completely digital. Today, everyone is digitally accessible. And the challenge is you cannot remove something from the system. Many times I give this standard example where think about it. For some reason, a particular posture of mine, picture, I want to delete. In the past, it was easy. I had an album. There was a negative and few prints. If I destroy the negative and whatever remaining prints, I throw it away, then the picture is gone forever. But today, we upload it into so many places. It is there on your Instagram, Facebook, Telegram, and so on. And then you send email and whatnot. So even if you delete the picture from wherever you wanted, where all it got uploaded, we don't know. And many of the apps, we already signed up, given permission for them to keep our images. So whatever you uploaded, even if you delete, they will be keeping it. Sometimes it is a legal requirement because as an app provider, the app provider has to maintain for legal requirements for X number of duration. So your own picture, you are not able to control. You don't have the right to destroy once it is uploaded in a digital world. So your privacy is at stake because even if you don't want, it is available to somebody else. So ensuring cyber security, compliance, safety, privacy, availability in this emerging era has thrown up large number of challenges. In between time, there was something called information overload. So today it is going to that world. All document and data should be available, but it should be on need to know basis, not that anybody can upload anything and everybody can have access to everything. So it is the need to know basis concept that has to become part and parcel. And it is like, even if I trust you, I need to always verify. So however good the design document is, we need to always test and verify. Okay, it is like saying, I trust you, but checking is my duty. That is the way security guard does it. Otherwise, you go to your office or institute, you have the ID card, but still it is job of the security guard to check the vehicle and check the person. So even if it is fully trusted, we need to continuously test to verify and validate, because any of the variable in the environment could have changed. It could be a change in the legal requirement. It could be a change in the management. It could be a change in the operating system. It could be a change in the, what should I say, the use case. Who is going to use? So like that, there are n number of reasons why you need to test and continuously test. So yeah, probably looking at the time, since I missed seeing all of you, I will stop sharing. Now I'll go back to that Google window. Maybe switch on the camera. So I'm happy to take any questions or any discussion points. Yeah, I'm open. Thank you for your patience learning to start with. And I hope you have learned something, but you are free to throw questions from your side, whatever you want. Don't restrict to only what I spoke about. Yes, the floor is open. Well, if I'm not hearing anything, then I'll say a few more small things. See, I'm currently the person responsible for CDAC Bengaluru. I'm the executive director. I wanted to update a couple of things. By March, we are currently setting up a 650 teraflop supercomputer under National Supercomputing Mission, and that will be available specifically for your technology innovation hubs that you have startup that you have at your colleges. If any of you want to use that, they will be available starting April next year. And we also plan to offer certain specific training on parallel computing, high performance computing to academic institutes. So you are welcome to make use of that. And other than that, there are many other activities that CDAC does, but at least this I thought it is something pretty much new and you can go for it. So I have a question from Ms. Pramila Das. Please. Yes, madam.
Sir, actually, I made a program in MATLAB. Can you hear me? Am I audible?
You are audible. Please go ahead.
Okay, sir. Actually, I made a program in MATLAB. It was all about PSO, so particle swarm optimization. I made the programming, but all I wanted was to upload the programming in the cloud computing server of IoT. But I'm not able to do that. So, sir, do you have any suggestions? How can I upload that program, or how can I upload it in cloud computing so that I can access that program from any part of the world?
Yeah, I think if it is in the local server, whatever you have done the thing, basically you have to go for a standard process of having an account with a Google, any cloud provider. And then you should take the services to both for compute as well as, let's say, storage, all those things. And then they will allow you to upload. So basically you need to have an account with one of the cloud providers.
Okay, sir. What kind of account? Are we talking about iOS account, or that I have seen in my Apple phone that there is an option of iOS cloud computing? So, is that what this ID is all about? Is there? Do I have to upload the program there?
Yeah, you have to choose, madam, because today I think in one of the slides you mentioned the AWS, Google Cloud, like that. There are many cloud providers. Amazon is there. So there are also open source cloud platforms that are available. So you can actually go, for that matter, every phone, Android or iOS releases, they also provide the cloud option. You have to choose. It's like everyone is a vendor. You choose based on your capability, how much money you want to spend, or you want it totally open source so that it doesn't cost you much. So each one comes with some comfort level and discomfort level.
Okay, sir. Okay, now I understand. Thank you, sir.
Thank you.
Dear participants, if you have any queries, you can either post it in the chat box or you can unmute and ask.
Yeah, since questions are not going, maybe actually I'm very happy to see people across various locations. Going by the names, I can figure out different parts of the country. So definitely it's at least pan India, if not beyond that. That is extremely good to see. And you are also free to visit CDAC website and okay to I will share some of the part of it as a PDF file. It will be shared with Sitaraman sir, Professor Sitaraman. So you will get my email ID as well as some select contents for your consumption.
Sir, thank you, sir.
So thank you very much, sir. So I wish the very best for the participants and IIIT Trichy, and also Dr. Sitaraman for inviting me and giving me a chance to articulate some of my ideas. And in case if this was a little bit away from VLSI per se, please go ahead, and we can actually separately have a session only on the hardware at some point in time if required. But definitely it is an extremely good area. Only reason is doing VLSI security alone is not good enough. Whatever you do today, we need to have a global 360-degree view of the system, so that what you do fits into the larger puzzle. Because all we are looking is a small piece of the solution to a puzzle. So a entire puzzle should be moved. That is the reason, I thought, we thought of this session, and we covered this aspect specifically. And as I speak, we are actually involved in developing a indigenous microprocessor development program. There is a MDP, it is called Microprocessor Development Program, and CDAC is fully working on it. And very soon we'll have a complete indigenous hardware under that program. It's a mission mode program that is happening. So all of you also, maybe I do not know, some of you may be part of the EMDP program, where some 100 institutes are getting a Xilinx-based FPGA development challenge. Some of you may be even part of it. So that is being managed by CDAC Bangalore. Yep.
On behalf of Department of Electronics and Communication Engineering and Computer Science Engineering, IIIT Tiruchirappalli, I take this privilege in thanking Dr. S.D. Sudarshan for his valuable and informative session. Really, the session was so excellent, sir. Thank you. Thank you on behalf of participants also.
Thank you, sir. You all have a good evening and stay safe from Nivar.
Yes, sir. Thank you, sir. Bye, sir.
Thank you, sir. Bye-bye.
Yes, sir. Bye.